almost everybody that I knew prior to coming to CppCon has had nothing but good things to say about the conference and the quality of individuals that you'll see around here. Just try and take the plunge one year. You'll learn something 100% guaranteed.
Hi, everyone. Welcome to the last day of the conference. You've made it, almost. And welcome back from lunch. My name is Daisy Hollman. I've been super excited to give this talk for a while, which also means I'm super nervous because I really want it to go well because I want to give more of these. This is what can you learn from being too cute, what you should write, why you should write code that you should never write. And I'm calling it part 1 of N, because I submitted an outline for this talk that had 10 cute tricks in it, and this set of slides has 6. I presented 4 of them or 5 of them last night, and it took me an hour and 45 minutes. So we have no idea how many talks this is gonna be broken up into, but I'm excited, and I hope this goes well enough that we can keep doing this at a few other conferences and just keep learning interesting things about C++. But why? So part of this is we're all at the end of the week. We could all kind of use a laugh at ourselves at C++ with C++, laugh, yeah. And sometimes you do have to laugh to keep from crying. I hope everyone can learn something new about how C++ works from this talk. Particularly by using it in a way that's so bizarre that you can't forget how it works when it comes up in real code. And then maybe also learn the right way to do the same thing, at least for a few of these. And more importantly, I hope people will learn how to learn these things, how to play with C++. That's how I've learned so much that I know about C++. That's how I got involved in the C++ committee, is to play with C++ like this. Not in real code bases, not in production code, but how to learn new things about C++ by playing. So disclaimers, don't use these tricks directly in real code. I know someone is going to cite this talk in a code review, so I'm going to give you a snippet right here, right now, that said that you can respond to them with saying, don't use these tricks in real code. And don't cite this talk in your code review. But do use these things to learn things about your existing code. This is very definitely not a software engineering talk. This is not about what you should do in real code. This is about how to learn new things about C++ for people who have been doing it for years, people who have been doing it for decades. I hope people who have been doing it for decades will learn new things from this talk about C++. I learned several new things while writing this talk. Several people on the committee have learned new things because I had to ask them if this is how this works, and they said, I don't know. But yeah, well-written code should be unsurprising, and the whole point of this talk is to share some snippets that are surprising and then learn about them. So I do have a problem of my talks getting a little bit too into the weeds, but sorry, this talk is all weeds. And this talk is actually several mini talks. And I'm going to ask you to hold your questions to the end of each subsection. It's kind of broken up into like tweets that I made and then kind of follow-ups on that. And there's 6 of them. I won't get to all of them, but I'd ask if you'd hold your questions to the end of each like mini talk, unless I specifically ask if anyone has any questions or something like that. All right, really quickly, my qualifications. Who am I? Well, I'm Daisy, so I'm responsible for all of the oopsie daisies on the committee, but I regret nothing. Titus once said that he agrees with me, so that I think makes me an expert at software engineering, and he said so again at lunch on Tuesday, so that, you know, Bjarne once said +1. But then on Monday, Bjarne also said that he hates this talk. So if you go back and watch his keynote, he essentially said that. So, and Titus once said that a feature I proposed was nuclear weapons. So you can take what I say with a grain of salt. Anyway, here we go. So this is my first trick. I tried to roughly organize them a little bit by kind of popularity in terms of likes and views on Twitter. And I'm going to jump around through them. I'm putting the actual tweets into the talk so that you can go back through when I put out the slides. I'm going to tweet out the slides after the talk. You can go back through and click on the tweets, look at the conversation around the tweets. There's actually quite a bit of interesting stuff going on there. But I'm going to put the actual code and the trick here so that people can actually read it. So this is a kind of a fun one. You can iterate backwards through a parameter pack by folding over a right associative operator like assignment. So if you don't know what a lot of those words mean, hopefully by the end of this set of slides you will. But don't worry if you don't. So I think well, it turns out it's not actually the associativity, but we'll get into that in a second. So I think the thing that surprised people so much about this particular trick was this kind of surprisingly compact piece of code that does something really weird, right? So we're doing a fold expression over a couple of different operators, the comma operator and the assignment operator, right? And they do opposite things, and that just seems really weird to people. So I'm going to walk through this a little bit. This is, often you'll find yourself when you're doing generic programming in this situation where you have a single name for a parameter pack, right? T's with the lowercase t is a name for our parameter pack that represents multiple actual arguments, right? And you need to somehow do something with all of them or do something with some of them. And this is going to be a recurring theme in the talk, actually, because these are some of the hardest things to work with in C++, and thus they have some of the most surprising behaviors. So we have a little lambda here just to show off, like, what's going on, that actually prints out the argument to the lambda and then just returns something that we can use with the assignment operator. It doesn't really matter what it is as long as it has a well-behaved assignment operator. It doesn't do something weird with the assignment, like you couldn't return something that has a deleted assignment operator. But I use the type identity because I think that's an interesting C++ 20 feature that everyone should know about, but I'm not going to talk about it here because that's beside the point. And then we're gonna do this fold here. And when we call this function template that we've created with a parameter pack, like 1, 2, hello, 3, 4 world, right? Notice that we can mix types in parameter packs. That's kind of part of the point, right? The assignment prints backwards and the comma operator prints forwards. And so I got some really interesting reactions to this, which maybe I should have put this into my qualifications. Alistair Meredith said that he wishes he'd figured this one out himself. Michael Park, terrifyingly enough, says that he's used this in real code. And other people said this is witchcraft, which I hope to fix. I hope this doesn't look like witchcraft by the end of this talk. So what's going on here? Let's walk through this very slowly without parameter packs. So we have this print1 function. It returns something that we don't care about, right? We're just ignoring the return value here. But we are printing things out with cout. Yes, I use indel here because I, at the time, worked in a field that didn't do much input-output, and I didn't realize that that's a thing that people say you're not supposed to do, and that's not part of this talk, so anyway. So obviously if I call print1 with hello, it prints out hello. If I use the comma operator, so the comma operator is something that you generally shouldn't use in C++. That comes up occasionally, but we get hello printed first and world printed second. And if we use the assignment operator, we get world printed first and hello printed second. And what's going on here is that we're evaluating the arguments to an operator call, right? So in the first case right here, This is where you have the comma operator, and in the second case, the equals operator. But the evaluation of those arguments has side effects, right? And for a long time C++ programmers will know that in general, the side effects of function call arguments, the ordering's not specified, right? I got a very interesting reaction from Sylvester Hesp. And if you're here or you see this, thank you for this reaction. It actually made me dig into this a lot more. I appreciate it. They say that operator associativity doesn't apply here. The type of the fold expression actually determines where the parentheses go. And that's actually a really good point. But it turns out that I was lucky enough to be wrong, but kind of right. And that the associativity of operators, we've mostly fixed C++ to the point where the associativity of operators indicates the order in which its arguments are evaluated. So I'm going to go back over that in a second if you didn't catch it the first time. But if you did, then they also point out that, well, except for the ternary operator, which does evaluate the other way, even though it associates right to left. So operator order of evaluation. If you're not familiar with the term associativity, this will help hopefully give you some idea of what's going on. We're going to step back a second and look at the actual standard. This is the statement that Sylvester was pointing out, and that is that, you know, the arguments to individual operators are not sequenced, the evaluation of the arguments, right? But in C++ 17, we actually added that for the comma operator specifically, the left expression is sequenced before the right expression. And then also in 17, in the greatest stable tag in the entire standard, expr.as, we added that the right operand is sequenced before the left operand for assignment. So let's talk about fold expressions and associativity and see what Sylvester was talking about here. So if I have a parameter pack, so I'm just using these lambdas here as a way of like conjuring up a parameter pack, right, that you can see exactly what's going on. And I expand with the dots on the right. That's equivalent to grouping parentheses from right to left, right? So it's called right associativity, or a right fold. And you can remember that because the ... being on the right side means that there's more parentheses on the right side. And so these two are equivalent and actually have equivalent outputs here. If I do a left fold, put the ... on the left-hand side, right, that's equivalent to grouping the parentheses on the left side as you unpack the expression, right? And so you can remember that by the ... being on the left-hand side means that there's more parentheses on the left-hand side. But in this case, we actually get the same output for all of these. And that's because the associativity, as Sylvester pointed out, is not the actual reason why the output is this way, right? There's more going on here. If we do the same thing with the comma operator, we get the same result backwards, right? We get the 1 and then the 2 and then the 3. And so I thought I'd put that in here for completeness. Let's dive a little bit deeper into order of evaluation and see if we can understand what's really going on here and what the difference here between associativity itself and the mnemonic that right associative operators evaluate right to left. So here we have this, this is, by the way, a good way to learn anything you want to learn about C++. If something's happening that you don't know what's happening, go into the customization point that's being called, whatever it is, whether it's the operator or a coroutine or whatever, and just start printing things out and see what happens. Debuggers are also quite useful, but debuggers don't do very well at stepping through code that's not there. So anyway, we have essentially the same thing, except for instead of printing out just random strings, we're going to print out this, we're going to return this blabbermouth class that it has a special assignment operator that prints out the data member name that's associated with it, and then assigns the data member name to be a new string that says, where it came from, right? And then we're going to just do the same thing we did before. This is a write fold on print1, right? And we see that we get print1 of C and print1 of B evaluated first. So that's this part in the parentheses right here, right? So the right argument of this full expression is being evaluated before the left argument of this full expression, right? And inside of these parentheses, the right argument of this expression is being evaluated before the left argument of this expression, right? So then the next thing that happens is that this is evaluated, right? This equals operator is evaluated, and that has this print statement in it, right? And then after that, we actually evaluate the left-hand side of this full expression, right? So these parentheses are the right-hand side of this equals operator here, right? And so it gets evaluated before the left-hand side of this equals operator here. So we actually are evaluating the assignment in here before we actually evaluate print1 of A. And then we evaluate the final assignment. And you'll see that if I go the other way around, we actually do see a difference this time, in which now we're actually evaluating print1 of C. And then we need to evaluate the left-hand side of this operation before we can actually evaluate the operation. So evaluating that entire left-hand side here involves first evaluating this, print1 of B, and then evaluating print1 of A, and then evaluating the assignment operator. And then we can finally evaluate this assignment operator. So did everyone follow that? We're at the end of this trick. Are there any questions that I can answer for this particular trick before we move on? Any online questions related to this trick in particular? Are people mostly following? All right. I'm trying to take it slow, but I do have a tendency to get super excited and talk really, really fast. And I'm sorry if I'm doing that, please slow me down. All right, let's go on to a completely different trick. This is the one that I put up on the screen during my practice talk, and one of a very senior engineer watching my talk said, "Oh, I do that all the time." So maybe this is something you should do, maybe not. I still think that you should use something that's a little bit more readable. But so if you want some block of code to execute exactly once in the lifetime of your program, even the presence of threads, you can put it in an immediately evaluated Lambda with a potentially unused static local variable. So what does that mean? So here's the actual code of our cute trick. We are running some function on a whole bunch of threads, in this case 2, because that's what Compiler Explorer supported at the time. But you gets the point across, and then we're joining those threads. And inside that function, all we're doing is assigning to a static block scope variable or static local variable a lambda that is evaluated and returns a value that we don't actually care about, right? So this is actually pretty easy to figure out what to do in this situation where you want to run something exactly once and it returns a value that you care about. But if it's a value you don't actually care, like if it's something that you want to run exactly once and it doesn't return anything, then people all of a sudden forget that you can also do this. And this is because it's in the initializer of a static local variable. And I'm going to go through exactly why and where the standard guarantees that in a minute. But first let's walk through some even more simplified version of this. Let's walk through the assembly and see what's actually happened here. So I'm going to take this into a form that I can actually kind of walk through it a little bit more, but it's the same thing as the previous slide from Compiler Explorer. So in this version, we're actually only going to, instead of printing something out, because that would generate a whole bunch more instructions, we're just going to increment some global variable, because that's like something that's easy for us to pick out in the assembly, right? So what the first thing the compiler generates is this it's loading a byte pointer to a guard variable for foo unused, which is this variable. So what do we mean there? So the compiler has actually generated a guard variable for this, right? That says if this thing is, it's a mutex, it's a protector around this thing, right? That it can only get executed, so that it only gets executed once. We're checking that variable, we're checking that guard variable. And if it's already been set, if it has not already been set, we're going to jump to this block of code that calls the initializer and sets this guard. And otherwise, we're just going to go ahead and return, right? Because there's like actually nothing between lines 6 and 7. So here we can see the compiler's actually generated the code to load the guard variable and call this internal function called CXA_guard acquire. Now I won't talk through what exactly that does, but it basically ensures that the guard variable has been acquired, right? And then we're going to test whether we successfully acquired the variable. And if we didn't, that means somebody else executed this before us, right? And then finally, we have in here, we have our code to actually increment the global variable. And then we call CXA_guard release with this guard variable, right? And return via tail call, basically. So is this something you can count on? Every time I post something like this, people are like, wow, this is crazy. I didn't know the compiler was doing all that much stuff. Is this something I can count on all compilers? That doesn't seem like something I count on all compilers. It just seems like this one compiler being safe. And no, actually, the standard says that dynamic initialization of a block variable with static storage duration is performed the first time control passes through its declaration. And there's a bunch of other text there that ensures that we know exactly when the initialization is complete. And then when I was making this slide, I was like, oh, wait. What does happen if the initialization exits by throwing an exception? That gives me a really bad idea. So then I tweeted. If you want some block of code to execute exactly n times in the lifetime of your program, you can use the same trick. But the first n-1 times, you can exit via an exception. And so that's this code. So we have, right here, we have exactly the same trick as last time, right? This is basically the code from the trick last time. We're just going to add a little bit to it, and we're going to, so we're going to catch this like custom exception type. It doesn't necessarily have to be a custom exception type, but if you want to be, absolutely careful about the code that you should never write, then that's one way to do it. And we're gonna initialize a static block local variable that's local to the actual initializer of unused, right? That's count. And we can, because we're between these opening and closing curly braces of this immediately evaluated lambda, we know we're executing exclusively, so we don't have to do anything with atomics or atomic increments, or there's a tiny, tiny asterisk on we don't have to there, but I'm not going to get into that. It may be a defect in the standard. Anyway, but we're going to just increment our count. And if we haven't run the number of times we want to run, we're just going to exit of this initializer via an exception so that we know that the next thread that reaches this will try and initialize things again. And so if we run this with, 2 threads that are calling foo 100 times, we see that we still only get the output 3 times, right? So it's to execute thrice. But we could also make exclusive execution because there's, no other really good way to make mutually exclusive execution in the standard library. Thank you for the 2 people who laughed. And instead of counting, if we just always exit via an exception, then we know that this function is always going to be called exclusively, and there's not going to be any race conditions, right? We're incrementing a counter here, and normally we'd have to do that with atomics, but because we're calling it from within this static initializer, we know that it's going to be called exclusively, right? And we don't have, and if we run this, we get, no race conditions, which is pretty nice. So what should you actually do if you want to do these things in real code? So I think many of you will know this, but not everyone. And so this is trying to target a bunch of different levels here. The name of the function that you use if you want to call something once in the lifetime of a program is std call once, which is a pretty good naming when. We don't actually have to return true here. I just left that in to so that you could see that it's the same function that we were doing before. And if we want exclusive execution, we have a thing called a mutex, which gives you mutually exclusive execution. I made a joke about it that 3 people laughed at, so foreshadowing. And you get exactly the same semantics as the trick that I showed before. And these two are really the things you should be using in production code if you want these same semantics. Because somebody's going to read this and say, oh, what's going on? Oh, I'm calling it once, right? Whereas someone who doesn't know how static initializers work may not realize that that's being called exactly once. So in general, writing code that has the name of what it does and the name of the function is good practice. And finally, if you want to execute something the first n times in real code, you should probably rethink your life decisions. But if you really do, you can just use an atomic and a mutex. And someone reading your code will know what's going on for the most part. So let's see, what are we at? 33 minutes left. Are there any questions on this section before I move on? Any online questions? All right. Oh, hey.
How does the code generation differ for creating a static variable versus std call once?
I did not look at that. We did specifically look at the fact that the exception behavior of std call once is the same as the exception behavior of entering a static initializer, static local initializer, and exiting via an exception. I would be surprised if their code gen is not similar. If it's not, then that's probably a compiler bug. Since the semantics are supposed to be identical according to the standard, you should talk to your compiler implementer and tell them to fix that if one is faster than the other. Any other questions? That's a good question, thank you.
So since the variable is static, I was wondering if it's actually once per compilation unit, or if it's really once per program, and if making it inline would fix that. And also how std call once relates to that.
So static in this case is, it does relate to the translation unit, but this, because of the one definition rule, those are deduped at, unless you define them multiple times, in which case you have an ODR violation in your program, right? Hey, Arthur.
Hello. To the previous questioner about the difference between call once and static in terms of performance, I think you'll find the static stuff usually does better code gen than call once, because call once will often be like pthreads or something like heavy, very heavyweight.
That is actually true, yeah. Pthread call once is often used for std call. You're right about that, thank you.
Oh, yes, and 2 from online. How does the generated assembly compare between the exception version and the mutex version? And doesn't the static mutex effectively lock guard twice, once to protect the mutex in it, and then once in the mutex itself?
That is true, although I believe mutexes are not dynamically initialized. So this is dynamic initialization of static variables. Somebody can correct me if I'm wrong on that, but I think it's a quality of, okay, but mutexes should be statically initialized, which means they don't need to be protected. But that is a quality of implementation issue.
Are static initializers guaranteed? Just like, is that a property of static initializers that they're guaranteed to be run exclusively and like not interrupted?
Yes.
Okay.
So that's this, it's, kind of a little bit obtuse in this particular block of code, but it's statement.decl, because this is how I read all of my stable tags. We see that anything that is a dynamic initializer, anything that has effects that are noticeable at runtime, will be performed the first time control passes through the declaration, right? So the actual mechanism for doing that isn't specified. Every compiler I've looked at uses this guard variable and then CXA acquire, guard acquire. But as long as it guarantees those semantics, the compiler is allowed to do whatever it wants.
The mutex has a const per default constructor, which means that the static initialization is guaranteed.
That is good. I did not realize that. I don't know, really didn't realize when we const expert all the mutexes, but that must have been in 17 or 20. Mutex is not the first thing I would have had on my list to const expert, so well done, WG21. All right, I'm gonna skip, oops, that's not what I wanted to do. I'm going to skip to trick number 5 and then come back to 3 and 4 because of where we are in time. But this one kind of stands alone and 3 and 4 kind of go together, and I don't wanna. So this is deduction guides for aggregates, and this was quite the adventure. Thanks to everyone watching who went on this adventure with me over the past few weeks. I learned quite a bit about the standard. The standards committee learned a little bit about the standard. We're filing a defect report. So the original cute trick was C++17 deduction guides can be used with class template argument deduction to make it easier than ever to use the rule of 0 for constructors, even for classes with relatively specific template parameters to deduce. So this is a simpler version of that, and I'll show you the more general version of that with like some more complicated version. But if we have this class template foo, right, that has data members that are dependent on its template parameters, right? We can add this thing on lines, oh, I don't have highlights here, okay. We can add this thing on lines 6 and 7 called a deduction guide that basically tells the compiler how to deduce the template parameters when class template argument deduction takes place. So class template argument deduction is when you construct a template without giving template parameters. So there's no angle brackets here. That actually looks like, pretty normal code for people who are afraid of angle brackets to use. Not that that's a bad thing. Any good programmer should be afraid of angle brackets, at least at first, until we have to use them. And you can see that like this code compiles and runs and has no problems. It deduces the type, in this case, to be int and char. It deduces the type in this case to be double and const char 6 because hello has a null terminator there, right? And so we've written something that is really very compact, very simple, and actually very generic all at once. And so I think that's actually a pretty nice little trick. And I actually, if you think the person reading your code is going to understand it, suggest you use it in your code. That's a very big if, right? Every piece of code you ever write should be with the person reading your code in mind. And if you don't think somebody's going to understand it, then go the long way, write a regular constructor, write a deduction guide. Don't be this cute. An innocent question. Wouldn't it be really nice if we could just omit the deduction guide, right? Pretty much, this seems a little bit redundant, right? The whole point of an aggregate is that you can leave out the constructors, and the whole point of aggregate construction is you can leave out the constructors, right? So who thinks we should add this to the C++ standard? Anyone? Okay, a few people do. Including a standards committee member. Awesome. Who thinks I'm adding leading questions about something that's already in the standard? Thanks, Teamer. Teamer wrote a paper that added this to C++20, and I didn't know about it. So I would have raised my hand on the first question for sure before this week. And actually, you can do this in C++20 code. You can just leave this line 6 through 8 out, and everything will still work. You get the expected behavior for class template argument deduction. You don't need any angle brackets down here. Yeah, so you get the trick without the extra cost. Well, the caveat is that this works fine with C++20 as long as _CPP deduction guides is greater than 2019-07, which Clang does not yet set. So if you are using Clang, you cannot yet use this. But GCC does fine with this. Presumably Clang will at some point. All right, let's go on to the original text of the trick that I tweeted. Well, you can actually do some fairly advanced things here, right? You don't actually need to translate your template parameters directly into data members like this, right? You could say, if I get an initializer, an aggregate initializer, that has an initializer list here, which is a valid way to construct a std vector, right? So that initializer list just gets passed to the std vector constructor directly, right? If it has an initializer list here, which is what the compiler interprets this thing as, then I want you to deduce u as the second template parameter, right? The values in the initializer list. And we're not even using u as the type of the second member. We're using u as the dependent type of std vector, right? The template parameter to std vector, the template argument to std vector. So that's, I mean, pretty cool. You can kind of go a little bit wild with this as long as you're still doing aggregate initialization, right? You can deduce pretty much any template parameters you want to with CTAD, which I think is pretty cool. And you still have this clean design where you don't have any constructors that you have to write yourself. You don't have to do anything that makes this not an aggregate anymore. All right, so question. Who thinks that this should work? Because I didn't have a clue. What if I want to use C++20 designated initializers with aggregate initialization like this? Does anybody think that this should work in C++? Who thinks that the standard says this shouldn't work? Who thinks that this is a defect in the standard and the standard's not clear enough? Oh, Teamer thinks that. Oh, wow. Yeah, so this fails to compile in Clang. So my first pass at writing this slide said, well, but Clang doesn't set CPP deduction guides to greater than 2019-07, so it's okay. Both compilers, both of those front ends are compliant. Both GCC and Clang are compliant on this. But yeah, this was another committee oopsie daisy. And this is guaranteed to work by C++20. There's language in there. I'm not going to go through it because I'm a little bit short on time and I want to get to what's actually my favorite part of the talk, which I put at the end so that I, wouldn't spend the entire time on it. And this bit of wording says that if there are no deduction guides, then a whole bunch of other stuff, and then basically treat an initializer list or a designated initializer list the same with respect to CTAD. But there's no actual wording that says if we have deduction guides, which deduction guides basically add to the set of overloads more or less, and the compiler performs overloaded resolution. It's not exactly like that, but that's one way you can think about it. And the standard doesn't say what happens with respect to overload resolution if the arguments are designated initializers because, well, usually arguments are not designated initializers. That's only for aggregates. Okay, so once we clarify this, should this work with deduction guides or not? Probably or not. The short version, and this is like literally the past 2 days, back and forth emails with some committee members over this. Basically, overload resolution is hard, and incorporating designated initializers might actually make it impossible, or very close to it. But this is ongoing work as of this morning, even. There's 2 emails in this thread that I have yet to read even, so maybe this has entirely changed in the past 30 minutes. Okay, let's go to talk more about parameter packs, because we started with that, and I'm gonna jump into this trick here of enumerating a parameter pack. So before we jump in too much, the quote from Eric Niebler, parameter packs are the compile time data structures of choice. As of C++11, C++ has language support for lists of types, and we would be foolish to work with anything else. So this is actually more in reference to older metaprogramming libraries that constructed lists of types recursively. And now we can just do this with parameter packs directly. So if you want to do any kind of metaprogramming at all, and a fair amount of just non-metaprogramming regular use of templates, knowing how to work with parameter packs is incredibly valuable. And I think I've already kind of driven that home in one of the tricks, but let's start with something that should be relatively easier, I would have thought. Iterating over or enumerating or indexing into parameter packs is perhaps one of the most difficult tasks. The greatest discrepancy between how difficult it should be and how difficult it actually is. C++ makes this a lot easier. There was some discussion for a while about having language level syntax for this, like a for ... I think is one of the proposed syntaxes. I don't actually know the status of that proposal, but I haven't seen it in a couple of years, so I suspect it's more or less not making much progress. Somebody can correct me either in the comments or afterwards, if so. But basically, we're in this situation where we're doing some generic programming, and somehow we have something associated with a name args, that represents a whole bunch of arguments, right? We call that a parameter pack, or an argument pack. So Herb already stole my thunder on this, but everyone in here who went to Herb's talk should know this is a template, even though it doesn't look like a template and doesn't use the keyword template, right? Because in C++20, we have auto, which we can use as an unconstrained short concept syntax. And that is effectively the same as if I had an unconstrained template parameter there, right? I just don't have a name for it, right? It is an anonymously named template parameter, right? But I do have a name for the argument, which is what I care about here. So here's how, in this example, we're using this. We're passing it a function, and then we're passing it a whole bunch of arguments and having it walk through each one of them and print out the index in the pack and the value, right? Just something very simple. And the thing that made this way easier in C++ 20 is that now you can give explicit template parameters to lambdas. And I think I'm going to walk through this like 3 or 4 times, if possible. I have 16 minutes left. Woohoo! How much time am I supposed to leave for questions? Okay, so I can talk until the end of the 16 minutes. Awesome. Sorry for not being on top of what I'm supposed to probably already know. So in this example here, in this case here, right, we are giving explicit template parameters to a lambda, and then giving a parameter expression that the compiler then does pattern matching on in order to say what is the thing that should be associated with this parameter pack, right? So we're trying to create, really, 2 parameter packs, one named args and one named idxs, that we can simultaneously expand so that we get them expanding in parallel, right? We get an index and an argument, and we're calling the function with both of them, right? So we need a way to come up with a name, to generate a pack that has a name in the same scope as we have the scope args. And to do that, we use this std make index sequence, right? Std make index sequence will make a sequence that is this long, right? It's basically making an index sequence object. It's a little more complicated than that because index sequence is a alias template that aliases to integer sequence, but it's essentially what it looks like here, right? It's going to create an object of type index sequence, right, that has template parameters that are 0, 1, 2, 3, 4, ... up to the size, the number given here, right? And so we're constructing that, and we're passing that in to this lambda, right? And then the lambda is pattern matching when it does overload set, when it does overload resolution, and finding that if I give this parameter pack the name IDXS, make that be the thing that represents 0, 1, 2, 3, 4, whatever, right? Then this is a valid overload, and so the compiler does that, right? So did people catch that the first time through, or should I go and try this one more time? Once more, okay. So the goal of this is to create a parameter pack with a name that we can use in the same scope as this parameter pack args, right? So std make index sequence is a way to create an object or create an instance of the index sequence type that has as its template arguments the sequence of integers, non-type template parameters, integers 0, 1, 2, ... right? Up to the number given here. So the number given here is size of ... args, and that's the size of ... operator is a way of seeing the size of a parameter pack, which is, of the things to do with parameter packs, surprisingly easy. We just stuck it in the language. I don't know why we didn't stick more things in the language. That would have made sense, but we tried to do everything with the library, and this is where we're at. And I say we there the whole time because I was part of the committee for a lot of this, and it's just the way we work. And so now we're gonna instantiate an object here. We're going to call this lambda, and the overload resolution that the compiler does when it's trying to see if you can call this lambda will match against this pattern here and say that if I make this symbol represent the parameter pack of non-type template parameters here, then this object can be used as the argument to this function call, right? The compiler is doing some very basic pattern matching in order to do this, and we are now allowed to name one of those patterns as of C++20. In C++17 and earlier, you had to do this in a separate function, and it made the code a lot less readable because it's jumping all over the place, right? And so inside of here, all we do is fold over the comma operator, right? So we did a fold over the comma operator earlier, remember, and that always evaluates from left to right. And so we're doing the same thing here, except for instead we're calling the users function, and we're expanding over two parameter packs, right? Or two different packs, right? And the rule when you're expanding over multiple packs is that they have to be the same length, otherwise it won't compile. But we've guaranteed that they're the same length in this example, right? By saying that the size of args should be the size of the generated parameter pack here, right? And so what'll happen is they'll just get expanded exactly, hopefully this is what'll happen here is exactly what you would guess would happen. If you would guess something else, then that's on us. And we need to figure out a better way to explain this. But if you had to guess, what was gonna happen here, I think most of us would guess that both parameter packs would get expanded in the same way, right? Certainly that was my first guess when I first saw this. And so, yeah, the function gets called with 0, hello. It gets called with 1, 42. It gets called with 2, world, and 3, 73. So did people mostly follow that? That is a It's going to be important to the next few slides. That's the trick that we use, that's the base trick that we use for pretty much everything in the rest of this talk that I'm going to talk about, because I only have 10 minutes left. That's the base trick that we use to interact with parameter packs in interesting and novel ways. All right, so let's look at another thing we could do with that exact same trick, essentially. We can index into a parameter pack. This is something that should be way easier. We should have just used square brackets. I don't know why we didn't just use square brackets. But we didn't. So this is, we have a size of operator but to get the size of a parameter pack, but we don't have a way to get a specific element of a parameter pack. And so we have to do something like this. We have to, here's one way of doing this. Oh, by the way, Louis Dion has one of my favorite recreational C++ blog posts I've ever read. If you're at all interested in this in more detail, read this blog post. It's absolutely fantastic. It's exactly how we should be thinking about metaprogramming. I hope going forward more people will write examinations of metaprogramming techniques that do this much and this thorough of an investigation, particularly involving benchmarking. I think more people need to do benchmarking of their metaprograms. Anyway, so we're doing the same thing, right? This is the same thing from the last slide. But instead of expanding over the comma operator and wanting to call each thing for each index, we're just going to call it, we just want something that calls a function for a particular index. Well, this is, once you know that trick, this is actually much more straightforward than you might think. We can just, instead of evaluating the user's function, we can evaluate a function like this that says, well, if const expr, we want to use if const expr here because we don't want to generate overloads to the user's function that may not be valid, right? If const expr idxs equals I, right? So we're just using this parameter pack in its pre-expanded form, and then when it gets expanded, it's going to get substituted into this expression here, right? We're using this parameter pack alongside a template parameter up here, and alongside an argument pack to the function, right? So we have, and when we expand this over the comma operator, we get the evaluation of this function for, because it's an immediately evaluated lambda here, right? We've evaluated it. We get the evaluation of this function for each entry in the parameter packs that are involved. Again, they have to be the same length, right? If you try and put two different parameter packs in here that are of different lengths, and then we put a ... the compiler will complain. But this is, hopefully, you can see this is not all that different from the previous trick, right? And it all goes back to this, right? This being able to deduce, to pattern match this ... here to get a name for the indices. So I have one more, I have one more that is more along the lines of parameter packs, and I have about 6 minutes, but I think this one is beautiful and cute, and I might go through this one a little bit faster so that the people who have maybe seen the previous stuff and are familiar with this will see something new and interesting. I thought this was fantastic. I was immediately, Richard Smith showed this one to me just kind of on a lark off of one of my other tricks, and he just kind of threw this in there as a way to do something that was completely unrelated to the trick, or not completely, but so another thing that you would think would be easy, and it isn't, is getting the last element of a parameter pack, right? So if we want the first element of a parameter pack, that's easy. We can pattern match by giving an explicit argument, right, and then a pack argument, and the compiler will match a parameter pack over that. But we're, for unknown reasons to me, not allowed to give a parameter pack and then a explicit last argument, right? We can't the compiler can't match that pattern for some reason. I'm hoping that as we start to get more and more sophisticated, like language support for pattern matching, we'll be able to match things like that at some point. But for now, you have to do something like this. Here's one way of doing it. There's a lot of ways of doing this. I thought this was really cute. So we're in this situation like we often are, where we have a set of arguments, right? And we need some way to invoke something that uses only the last argument for some reason, or we need some way to get a name for the last argument, right? And we're using our trick from before, but this time we're using something slightly different. We have a -1 here, and that means that our parameter packs are not going to be the same length, right? So we cannot simultaneously expand them. We're gonna have to do something different. And the something different that we're gonna do here is actually, I think, really cool. We can take a concept. So this is a C++20 concept. This one's pretty trivial. It actually is a concept that always passes. It's always true, right? Any, that's why we named it any. But it also takes this second template parameter that is a size and just ignores it, right? And you're like, well, why would you even write that? Well, we can expand a parameter pack in a set of, in parameters itself, if we have that pack in scope, right? If we have that pack in scope, and if it is a constant evaluated pack. If it is a constant expression, somebody's gonna give me the right term for that afterwards, maybe down in the comments on YouTube. Anyway, we have IDXS, it's always been part of a template here, right? And we can expand this pack over the first n-1 parameters to this lambda, right? And because we're no longer deducing the parameters, but we're actually telling it how many there are, right? We're not deducing the size of this pack. We're telling the compiler how many of them there are by expanding this parameter pack. We're now, all of a sudden, allowed to explicitly name the last argument, which I thought was really cool. It kind of feels like cheating, but you're allowed to do this. And then we call this lambda with all the arguments, and we now have a name for the last argument, which we didn't have before, right? So I think that's actually a really cute trick there. I wish I had time to go over it again, but that's essentially all the time I have to talk about this. One quick note, why can't we have nice things? You know, here's one way where this would be a lot nicer is if we could just deduce the arguments and then just deduce the second to last parameter and deduce the last parameter, right? That seems like code you should be able to write. And I spent a fair amount of time talking to committee members, talking to a bunch of people about this, and tried to do some archaeology on the papers. And even Corentin is actually writing a paper that would allow us to do this. Among the other, I don't know, 75 papers that he's writing. So if you want to see things like this in the standard, talk to Corentin on Twitter. He could definitely use some help writing papers. So in summary, why can't we have nice things? The closest thing to a good answer on this I got, though, was that people wanted to make sure that you could parse parameter packs in a single pass left to right, and there's some nice properties from a theoretical perspective of that that gives you. I'm not going to go into that any more than that, but yeah, that's all the time I had. So I didn't even take the time to make a question slide, so I'll just use the title slide. But questions?
Can you go back?
It's okay, Matt. I know you don't want people to clap for me, but.
Clearly. Can you go back to the arbitrary index of a parameter pack slide?
Maybe. Arbitrary index of a parameter pack slide. That is trick 3 slide, this one.
Can you use size of ... to get the last element out of the parameter pack there without the extra jumping?
The size of ... to get the last element
where you're doing the const expr IDX is equals I, what if
Yeah.
you did
So this is a different version of the same trick, right? Yeah, you could always get, anytime you can arbitrarily index into a pack, you could get the last one. And actually you can, vice versa, right? You can use what I will, I guess, call Richard's trick to get, you can use this to index into a parameter pack just by changing this from -1 to like -4 or -3 or -n, right? And then having an arbitrary deduced parameter pack at the end here, right? So you can have this expanded parameter pack that's explicit, and then you can have a deduced parameter pack at the end, and you can get a name for an arbitrary spot in the pack. So both could do both.
That's monstrous. I love it.
I was just wondering if you've compared the compile time performance characteristics of this approach and the arbitrary index approach.
It's garbage.
Both of them?
Yeah, everything I've shown you in this slide is garbage from a compile time perspective. If you want to do fast template metaprogramming at compile time, ask someone like Louis Dion, ask Odin. I've done some of this in my MD-span implementation. It's not nearly as cute as this. It's actually pretty boring. You end up expanding things out by hand to a certain number of times that the compiler stops putting them in one data structure and starts putting them in another data structure. And you can do different amounts for each compiler, and you can get arbitrarily fast compile time. You can speed up your compile times a lot by using some of these tricks. They're often not very cute. I should maybe do a talk on them sometime, or actually someone who knows these things like Odin or Louis should do a talk on them sometime. It's a really fascinating area. Louis' blog post is a good place to start learning about it. But that's unfortunately not this talk. Ben.
I was wondering, the arbitrary index into a parameter pack, the trick 3 you just showed.
Yeah.
Do you know a way to index into a parameter pack at runtime that's better than this trick with ORing together, the result of the...
At runtime?
It was the if const expr slide. It wasn't this slide. Sorry.
Oh, I'm sorry, this one. Yeah.
Yeah, so...
At runtime.
If apply to index doesn't take 2 as its template arg, but as a runtime arg, then you can do a similar trick with returning either false or true from the inside lambda and doing a fold expression over OR.
Yeah, you can do this.
You know a better way than that, is my question.
So it depends on your constraints, right? There are several better ways to do this. Honestly, the way you should do this if you ever happen to have to do this in code and you don't have constraints on performance necessarily that you might lose from this is just shove all these things into a std tuple and use std_get. But the constraint on runtime is, can you generate the callback safely with all of the types that would be taken, right? Or do you need to only generate the overload for that? If you have all of the same type, if you know they're all going to be the same type, and there are reasons why you would have a parameter pack where you know they're all going to be the same type or convertible to the same type, just use a std array and then runtime index into that. There are a number of other tricks. I don't know one that has these exact constraints on it that works at runtime.
Thank you very much. This was an awesome presentation.
Oh, thanks.
Your last slide about your wishful thinking, where we could just put in what the last parameter was. One of the nice things that would do is with std source location, the way you're supposed to use it is put the last pack equals current.
Oh, that's a really good point.
And then so with stuff like format or any variadic function, you can't have a source location, which would be potentially useful.
Yeah, this is a very good point. Thank you. Yeah, this is more motivation for everyone in this room to go and message Corentin and say, I want to help with your paper, and not just by contributing something that says I want this. I want to actually write implementations. I want to write wording. This is how the committee works. People ask someone else if they want help, and you go write a paper. So everyone in this room can do that.
I might be misremembering this, but I think this source location use case is literally the motivation for Corentin's paper.
Woohoo!
I remember I was seeing it in there, just as a comment. Synergy.
I planned that. Talk Questions online?
Well, we're out of time.
We're out of time. Woohoo! Perfect timing. Thank you.